14 billion years ago, the universe was born. Everything you see, everything you are, everything that ever was, it all traces back to a single moment. But here's what no one tells you. The Big Bang wasn't the beginning. It might have been a middle. We've all seen the image. A tiny point of infinite density explodes outward, and suddenly there's space, time, matter, light. The universe inflates like a balloon. Galaxies form. Stars ignite. Planets cool. And eventually, on one unremarkable rock orbiting one unremarkable star, something opens its eyes and looks up and asks, where did all of this come from? It's the oldest question our species has ever asked. And for most of human history, the answer was some version of the same story. A god spoke, a cosmic egg cracked, a dream was dreamed. But in the 20th century, science offered something different. Not a myth, not a metaphor, an observation. The universe is expanding, and if you rewind that expansion, frame by frame, like running a film in reverse, everything collapses inward. Galaxies rush toward each other. Space itself contracts. Matter compresses. Temperature soars. And at some point, roughly 13.8 billion years ago, everything we can observe was packed into a region smaller than an atom. That moment, that impossibly hot, impossibly dense beginning, is what we call the Big Bang. But let's stop here, because the name itself is misleading. The Big Bang wasn't an explosion. There was no fire, no shockwave, no debris flying outward through empty space. There was no empty space for anything to fly through. Space itself was being created. Time itself was being created. The Big Bang wasn't something that happened in the universe. It was the event that brought the universe into existence. Or at least, that's the story we've been telling ourselves. And for decades, it was a very good story. It explained why distant galaxies are moving away from us. It predicted the existence of a faint afterglow of radiation, the cosmic microwave background, which we found exactly where the theory said it would be. It even predicted the precise ratios of hydrogen and helium forged in the first few minutes of cosmic history. The Big Bang model works spectacularly well. But there's a problem. A deep, uncomfortable, philosophically devastating problem that most popular science accounts quietly skip over. The Big Bang theory doesn't actually explain the Big Bang. It describes what happened after. It tells us how the universe cooled, how particles formed, how the first atoms came together. But it says absolutely nothing about the moment itself. And it says even less about what, if anything, came before it. This isn't a small gap. This is the question. Because when you rewind the clock all the way back, past the formation of galaxies, past the first light, past the first sight, past the first second, past the first trillionth of a second, you hit a wall. Physicists call it a singularity, a point where the equations of general relativity break down completely. Density becomes infinite. Temperature becomes infinite. The curvature of space-time becomes infinite. The curvature of space-time becomes infinite. And infinity in physics is not a triumph. It's a confession. It means the math has stopped working. It means we've reached the edge of what our best theory can describe. And beyond that edge, we are in the most literal sense blind. So when someone asks what happened before the Big Bang, the honest answer, the scientifically rigorous answer, is that we don't know. But that hasn't stopped some of the most brilliant minds in physics from trying to find out. And the ideas they've come up with are among the strangest, most beautiful, and most unsettling concepts in all of science. Let's start with the simplest possibility. Maybe there was no before. This was Stephen Hawking's position, and it's more subtle than it sounds. Hawking, working with physicist James Hartley in the 1980s, proposed something called the no-boundary proposal. The idea goes like this. We think of time as a line, a straight, one-dimensional track that stretches from the past into the future. And we naturally assume that if we follow that line backward far enough, it must have a starting point, a first moment, a beginning. But Hawking suggested that near the Big Bang, time doesn't behave like a line at all. As you approach the singularity, the distinction between time and space begins to blur. Time becomes something more like a spatial dimension. It curves, it rounds off, it closes in on itself. Imagine the surface of the Earth. If you start at the equator and walk north, you can keep going, and eventually you reach the North Pole. But the North Pole isn't the edge of the Earth. It's not a boundary. There's nothing beyond it that you're being blocked from reaching. It's simply the point where the concept of further north stops having meaning. Hawking proposed that the beginning of the universe works the same way. Time doesn't start at a sharp edge, it smoothly rounds off. And asking what came before the Big Bang is like asking what's north of the North Pole. The question itself is the problem. It assumes a framework, a before, that doesn't exist. It's an elegant idea, philosophically satisfying even, but it leaves many physicists uneasy, because it doesn't so much answer the question as dissolve it. And dissolving a question is not the same as resolving it. So let's consider a very different possibility. What if the Big Bang wasn't the beginning of everything, but rather a transition, a phase change, a moment when the universe shifted from one state to another, the way water shifts from ice to liquid? This is the territory of a concept called cosmic inflation, and it has become one of the most important ideas in modern cosmology. In 1980, a young physicist named Alan Guth was working on a seemingly unrelated problem in particle physics when he stumbled onto something extraordinary. He realized that in the very first fraction of a second after the Big Bang, we're talking about a timescale so small that no human metaphor can capture it, roughly 10 to the minus 36 seconds, the universe underwent a period of unimaginably rapid expansion. Not the steady, gradual expansion we observe today. Something far more violent. In this tiny sliver of time, the universe doubled in size, then doubled again, and again, and again. Before the first tick of a clock could finish, it had swelled by a factor of 10 to the 26, a number so large that if you wrote it out as a 1 with 26 zeros, the zeros would stretch past the moon. A region smaller than a proton was stretched to something larger than the observable universe today, all in less time than it takes light to cross a single atom. In C, the IN solved several deep puzzles that had been nagging cosmologists for years. It explained why the universe looks so uniform in every direction, because regions that are now billions of light years apart were once close enough to reach thermal equilibrium before being flung apart. It explained why the geometry of space appears so flat, because any initial curvature would have been stretched smooth, the way the surface of a balloon appears flat if you inflate it large enough. And it predicted a specific pattern of tiny fluctuations in the cosmic microwave background, ripples in the fabric of space caused by quantum jitters during the inflationary epoch, which were later confirmed by satellite observations with stunning precision. But here's where inflation gets truly strange. If inflation happened once, most versions of the theory suggest it should keep happening. Not everywhere at once, but in patches, in pockets. The inflationary field is like a restless ocean. In most places, the surface calms, and there, a universe like ours condenses out of the energy. But in other places, the storm never ends. Inflation continues, and in those storm-torn regions, new pockets form. New universes. Each one born not from a single Big Bang, but from the failure of inflation to ever fully stop. Hot dense, full of matter and radiation. A Big Bang. But in other regions, inflation continues. And in those regions, new pockets form. New universes, each with their own Big Bang, each potentially with their own laws of physics. This is the idea of eternal inflation, and it suggests something staggering. Our Big Bang may not have been the Big Bang. It may have been one of an infinite number of Big Bangs, each spawning a separate universe in an ever-growing, ever-inflating multiverse. In this picture, the question, what came before the Big Bang, has a concrete if humbling answer: more inflation, more universe, an endless self-reproducing foam of space-time, bubbling with new realities, stretching back not 13.8 billion years, but potentially forever. Now I want to pause here because I know what you might be thinking. This sounds speculative. It sounds like science fiction dressed up in equations. And you're not entirely wrong to be cautious. Eternal inflation is a prediction of many well-motivated inflationary models, but it remains for now beyond our ability to directly test. We can't see other bubble universes. We can't send signals to them. We may never be able to confirm or rule out their existence. And some physicists argue that a theory which predicts everything, an infinite number of universes with every possible configuration, ultimately predicts nothing. It's not falsifiable. And if it's not falsifiable, is it still science? This is one of the deepest tensions in modern cosmology, because it reveals something important about the question itself. When we ask what came before the Big Bang, we're not just asking a physics question. We're asking whether physics, as we understand it, is even equipped to answer. We're asking whether the tools we've built, mathematics, observation, experiment, can reach that far back. And we're confronting the possibility that they can't. But not everyone is ready to accept that limit. And some of the most radical proposals for what preceded the Big Bang come from physicists who refuse to let the singularity be the final word. One such proposal comes from loop quantum gravity, a theoretical framework that attempts to merge general relativity with quantum mechanics. In loop quantum gravity, space is not smooth and continuous. It's made of tiny, discrete units. Think of it as the pixels of reality, each roughly 10 to the minus 35 meters across. At everyday scales, these pixels are far too small to notice, and space looks perfectly smooth. But at the extreme densities near the Big Bang, the granular structure of space becomes important, and it does something remarkable. It prevents the singularity from forming. In the standard picture, rewinding the universe leads to infinite density, a breakdown. In loop quantum gravity, that breakdown never comes. Density rises, yes, but at a fantastically high but finite limit. The universe refuses to crush itself. Instead, it rebounds. The contraction reverses. The Big Bang becomes a big bounce. And what came before our universe in this picture is another universe. A previous universe that collapsed, reached maximum density, and then re-expanded as ours. Not a beginning. A rebirth. The Big Bounce is a captivating idea because it removes the singularity entirely. There's no moment of infinite density, no breakdown of physics, no wall beyond which we cannot see. The equations remain valid all the way through. And it raises a haunting possibility that the universe is cyclic, that it has been expanding and contracting, bouncing and rebouncing, perhaps for eternity. Each cycle erases the details of the last, but preserving the fundamental process. A cosmic heartbeat with no first beat and no last. There's another version of this cyclic idea proposed by physicists Paul Steinhardt and Neil Turok that draws on string theory. In their model, our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space. And it's not alone. There's another brain, parallel to ours, separated by a tiny gap in an extra dimension we can't perceive. Every trillion years or so, these two brains drift toward each other, drawn by a force that operates in the extra dimension, and when they collide, the energy of the impact is converted into matter and radiation. A Big Bang. The brains bounce apart. The universe expands and cools, galaxies form and die, and then slowly, inexorably, the brains begin drifting together again. Another collision. Another Big Bang. Another cycle. In this picture, time doesn't begin at the Big Bang. Time stretches back through an infinite sequence of collisions and expansions. The universe has no birthday. It has always existed in one form or another, cycling through phases of creation and emptiness like the tide. These are beautiful ideas. But I want to be careful here because beauty is not evidence. And the honest truth is that none of those proposals, the no-boundary proposal, eternal inflation, the Big Bounce, the cyclic brain model, has been confirmed. Each makes predictions, some of which overlap with observations, but none has produced a unique, testable signature that would allow us to distinguish it from the others. We are, in a very real sense, still in the dark. And yet there are reasons to be hopeful, because we are not as blind as we used to be. Over the past 2 decades, our observational tools have become extraordinarily precise. The cosmic microwave background, that faint afterglow of the Big Bang, has been mapped with such exquisite detail that we can read in it the story of the universe at an age of just 380,000 years. And encoded in that story are subtle clues about what happened in the very first moments. The pattern of temperature fluctuations, the polarization of the light, the statistical distribution of hot and cold spots, these carry information about the physics of inflation and potentially about what preceded it. We are still in the dark, but now we're beginning to read it. If inflation happened, it should have produced a specific pattern of polarization in the cosmic microwave background called B-mode polarization. Detecting this signal would not only confirm inflation, but would give us a direct window into the universe at an age of less than a trillionth of a trillionth of a trillionth of a second. It would be the earliest observation in the history of science. And different models of what preceded the Big Bang predict different signatures in this signal. Some predict it should be strong. Others predict it should be absent entirely. The data, when it comes, may finally allow us to discriminate between competing visions of the universe's origin. There's something else worth considering as we think about this question. Something quieter, more philosophical, but no less important. When we ask what came before the Big Bang, we are implicitly assuming that before is a meaningful concept. That time extends backward without limit. That every moment has a prior moment. But this assumption may be wrong. Not just practically wrong, but fundamentally wrong. If time itself was created in the Big Bang, if the Big Bang was the origin not just of matter and energy, but of the temporal dimension itself, then there is no before. Not because we can't access it, but because it doesn't exist. The question is like asking what's south of the South Pole or what's outside the universe. It uses familiar words in a way that feels meaningful but may not correspond to anything real. This is deeply counterintuitive. Our brains evolved to navigate a world where time flows steadily from past to future, where every effect has a cause, where every story has a beginning. The idea that time itself could have a boundary, not an edge you bump into, but a place where the concept simply ceases to apply, is almost impossible to internalize. And yet, this may be the reality we inhabit. Or it may not be. That's the point. We don't know yet, and there's something profoundly honest, even noble, about admitting that. Science is not a collection of final answers, it's a process. A way of asking questions with enough discipline and humility that the universe occasionally answers back. And on this question, the deepest question we can ask, the question of how everything began, or whether it began at all. The universe has given us tantalizing hints but no definitive reply. What we do know is this. Roughly 13.8 billion years ago, the observable universe was in an extraordinarily hot, dense state. It expanded, it cooled, structures formed. And here we are, a species that has existed for the blink of a cosmic eye, using instruments made of the universe's own matter to peer back at the conditions of its birth. We have mapped the afterglow of creation. We have detected the gravitational waves from colliding black holes. We have built mathematical frameworks that can describe the behavior of spacetime at scales so small that 100 billion of them would fit inside a single proton. And we are closing in, slowly but relentlessly, on the answer to what happened at the very beginning. Maybe there was a previous universe that collapsed and bounced. Maybe there's an eternal inflation field, endlessly spawning new realities. Maybe time itself curves and closes, leaving no room for a before. Maybe the answer is something none of us have imagined yet. Something so strange, so far from our everyday experience that it will require entirely new mathematics, entirely new intuitions, entirely new ways of thinking about what it means to exist. What strikes me most about this question is not the answers we've proposed, but the fact that we can propose them at all. That a species of primates on a small planet orbiting an ordinary star in one galaxy among trillions can look back across 13.8 billion years and ask, with any credibility, what preceded it all. That's it? We can write equations that describe the curvature of space-time at the moment of creation. That's it? We can build satellites to listen for whispers from the first fraction of a second. We don't yet know what was there before the Big Bang. We may never know. But the fact that we're asking, that we've built the tools and the theories and the courage to ask, is itself a kind of answer. Not to the question of what came before, but to the question of what the universe became after. It became, among other things, something that could wonder about itself. And in a cosmos that may be infinite, eternal, and indifferent, that small fact feels like it matters. The question remains open. The universe keeps its earliest secret, pressed into the oldest light, hidden in the math we haven't yet written. And we keep looking. Not because the answer is guaranteed, but because looking is what the universe, through us, learned to do.